Hey, good afternoon, everyone. So if you remember when I was welcoming you all last week, I talked about the importance of neutrino physics in the US particle physics program. And so really thrilled that Shirley Lee is here from UC Irvine to tell us about neutrino physics in the era of data.
Thank you. Can everyone hear me okay? Okay, so first, don't be alarmed by the slides. Majority of my talk will be chalkboard. Just in the beginning, a couple of slides. Okay, so again, my topic was neutrino physics in the era of data. So I think I'm hoping to cover roughly 3 topics per class. So today, I will be giving everyone an overview of the standard neutrino oscillation paradigm. And just to making sure that no one gets bored, I'll also talk about some of the subtleties in the oscillation formula. And then tomorrow, hopefully, I'll be able to cover basically just introduction of what is the neutrino nucleus scattering cross-section problem. So this is something that you might have heard people talk about, especially in the recent years. And it's more like, what is this issue? And lastly, in the third class, I'm hoping to discuss what kind of BSM scenario or astrophysics we're able to probe in neutrino experiments. OK, so let's get everyone on board. So I want to cover the standard neutrino oscillation paradigm. Now, I think it's safe to say that there are 2 kinds of audience right now. Either you have seen the very standard derivation, or you have not. If you have seen the standard derivation, then my task for you is I'll do the derivation on board in the slides. In the derivation, it's standard. I have made 2 mistakes. So pay attention and try to find those mistakes. And if this is the first time you've seen it, then enjoy. OK, so sorry?
Enjoy the mistakes as well.
Oh, yeah, it's quite fun. OK, so the standard neutrino oscillation paradigm that we have is that we have 3 flavor eigenstates from our standard model. That's the eigenstates in our weak interactions. So it's electron, muon, or tau. And pretty much all the time, the convention is we use alpha to indicate that. And unfortunately, fortunately, these weak eigenstates are not the eigenstates of a Hamiltonian for a free particle. So those are the what we call mass eigenstates. And we just call them nu1, nu2, nu3. And typically, they're labeled as nu I or k. And these 2 bases are not aligned. And so you can rotate between these 2 bases. And that's the unitary PMNS matrix, and written here. And the PMNS matrix can be divided into 3 sections. And it's 3 mixing angles, theta 2, 3. And so when there's the first mixing, if it's a 2 by 2 matrix, then we know the mixing matrix is cosine, sine, minus sine, cosine. So there's the 2, 3 sector in the first one. And there's a 1, 3 sector, which also has a delta CP violating phase there. And then we have the 1, 2 sector. So this is the standard decomposition. And again, later when we talk about phenomenology, we'll discuss each of them separately. But for now, just imagine this is a unitary by 3 by 3 matrix. So given this, what is neutrino oscillation? Now, really, this is the vacuum oscillation. It's just a standard 2-level system in quantum mechanics, basically. So the idea is, initially, however neutrino is produced, it's produced as a flavor eigenbasis. And we can decompose that into mass eigenstate.
Oh, sorry, I asked a question. I just forgot. So in the last slide, was the UPMS Hermitian or not?
It's a unitary matrix.
Sorry, oh, yeah, unitary. OK, thank you.
Mm-hmm. Which is also important, especially when lecture 3. Okay. So the standard assumption, it is a unitary 3 by 3 matrix. And once we produce the neutrino state, how it evolves, it's pretty straightforward. Because each mass eigenstates are, again, mass eigenstate of the Hamiltonian. So as they evolve, they'll just pick up a phase of e to the minus IET, right? And E is the energy corresponding to each mass eigenstate. So this tells us how the flavor state evolve. And what is oscillation is that I start with a new alpha, let's say either nu mu or nu E. And I let it propagate over some time, which is afterward it turned to nu alpha t. And then at the detection point, I want to see how much of this nu mu or nu e are nu mu or nu e or some other flavor. So then I project out into a different state to nu beta. And again, this is pretty straightforward math. So that is the oscillation probability. This is probably not what you're familiar with. So let's simplify this a little bit, because what is EK minus EJ? Because we know neutrinos are ultra-relativistic, because all the neutrinos, like, let's say a standard scenario you have in mind is, we don't exactly know the neutrino masses, but they're super, super light. They're less than 1 eV. And say in accelerator neutrinos, these neutrinos are GeV energy, so they're super relativistic. Then I can expand the energy of neutrino in terms of mass, and in terms of their momentum, and the correction corresponds to mass square. Okay. So then, the thing in the phase, which is the thing that's interesting in the exponential, the energy difference becomes the mass square difference over 2p. So this tells us that the oscillation probability looks like the following. It has some number in front, and that's either written in terms of mixing elements of u's, or more commonly you might see this as sines and cosines of angles. But the important thing is there is delta m squared over 2p, and as a function of time, and multiplied by time. Okay, all good? Okay, so just copy that again. And this is still not quite what we typically see, right? And again, we know that neutrinos are ultra-relativistic, which means they're traveling at speed of light. So then I can replace the time as L, and also their momentum is the same as energy. So then I substitute the term of L and P in my expression, and that is the standard 3x3 neutrino oscillation formula for neutrino to oscillate from any flavor E mu tau to any other flavor E mu tau. And again, the feature is there's a bunch of numbers in front, and there's a famous delta m squared L over E dependence in the oscillation probability. Any questions so far? Anyone spotted the mistakes yet? Yeah.
You have a magnitude squared, and you have something that can, in principle, be complex on the right side.
No, so right, so this is written not explicitly, but if you expand things explicitly, it's always real. For instance, oh, sorry, I just want to make a comment that, because I might use the phrase. Typically, we use the phrase that if you start with some flavor and you detect the same flavor, like muon neutrino to muon neutrino, it's called disappearance channel. If you start with a flavor like muon neutrino and oscillate into nu e, it's called appearance channel. So that's just a terminology that I might say. Okay, and this expression is not, if you are not super familiar with it, for like a two-level system. Let's imagine that instead of 3 flavor eigenstates, we have 2. Then this simplifies to the one on the bottom, which might be a little bit more familiar. But you just have to trust me on that. The numbers work out such that it's always real.
Okay, so you get like multiple e to the I.
Yeah. Yeah.
So why do we assume that they're like not necessarily in an energy eigenstate, but we do assume that they're in a momentum eigenstate? Like, why do we not have indices on the P?
Oh, okay, so great question. So this is the so-called equal momentum assumption, which I think you are. Do you have follow-up question? Let me ask that way.
That was my question too.
Great question. So if you think a little bit harder about this, so this is one of the mistakes that I'll elaborate later. But you're right. So so there are 2 things. So first, these neutrinos are assumed to be in their momentum eigenstate. It's a plane wave. Also in their mass eigenstate, also in their energy eigenstate, because it's a plane wave. So they do have definite energy as well. So that's question number 1. It's not like their energy of the mass state change, right? But your question is, why do I assume their energies are different? I interpret your question as, why do I assume E1 and E2 are different, but P1 and P2 are the same, right? So that is actually one of the mistakes I made, that I should not be making that assumption. Because if, let's say, we consider neutrino from pion decay to muon and nu1, and pion decay to muon and nu2. Obviously, this nu1 and nu2 have different energy and different momentum, right? Just from two-body kinematics. So that's one mistake here, that there's two ways to get a standard formulation, oscillation formula. One is assuming equal momentum. And you can see that another case is you assume they have different momentum, but assuming that they have the same energy. And that's called same energy, equal energy assumption. Interestingly, that would also get you the correct formula. But both are wrong, because neither is correct. I guess that's the same thing, but you get what I mean.
Isn't the equal energy one the one that's just correct because you're producing them with the same energy from the same source?
No, so equal energy one is also wrong, because you can assume, like, you have a pion, go to muon and neutrino. So if you just conserve energy and momentum at the same time, you will realize that their momentum and energy are both different. And this is something you can compute. So both are wrong, but both lead to the correct result. Okay, so mistake number one is found, great. And there's another mistake. And question? Sure.
So what is the right way?
Sorry?
So what is the right way to derive this correct?
Oh, well, I mean, you have to find the mistake first.
Why would momentum be conserved if there's a recoil particle that could absorb additional momentum?
Oh, so again, we assume let's take a simple production case of like pion decay to muon and neutrino. It's simple because, well, first, that is the production mechanism for like accelerated neutrinos, right? So it's realistic. And also because it's a 1 to 2 body, so it's simple to think about the kinematics. For like nuclear beta decay or something, it's a little more complicated. But let's just stick to pion decay. Any other questions, or anyone find the other mistake?
Yeah, if it's relativistic, the time is not same for both.
If it's relativistic, time is not equal for both. Very, very close. But not.
Travel different distances. The L will be different.
Let's say given that, but let's say experiment has finite resolution, right? We don't measure neutrino in our detector to infinite precision. They are a little bit different, but within the detector, I don't know, let's say 10 centimeter resolution, they're basically the same, right? So it has something to do with the time, but it's not exactly that. Okay, so any other questions or any other attempt at finding the mistake?
You're assuming they're traveling the same velocity.
I'm assuming they travel, okay, so I think it's a little bit similar. I assume they both travel close enough to the speed of light. And let's say, even if they might be a little bit different, let's assume that the difference is not, is within experimental resolution. Okay. Any other guesses?
Well, what's happening in the rest frame? Would you get a different look? Your analysis in the rest frame? You said it had to do with time, so I'm just thinking.
Correct.
Right. I mean, then they're ultra relativistic. Nothing. So no time is elapsing.
Correct. I think that's very, very close to what the real answer is. So let me just reveal it. Okay, so remember someone mentioned, and I also confirmed, that when we write stuff like this, we assume these neutrinos are in momentum/energy eigenstate, right? And what is the feature of a momentum eigenstate? That it's a plane wave. Plane wave is, what's the feature of plane wave? It's uniform everywhere in space, right? It changes as a function of time, but plane wave is everywhere the same in space. So if I assume things are a plane wave, then it doesn't make sense to say my neutrinos are traveling at speed of light, or neutrinos are traveling at all, because plane waves don't move. It's the same everywhere. So if I assume things are plane wave, then I cannot say it's not even the neutrinos have different velocity. If it's a plane wave, it doesn't have a velocity.
Plane waves still have velocities, even they do.
Well, if it's just literally a plane wave, let's say momentum eigenstate, then the plane wave would be e to the IPX. That doesn't have, e to the IPX is everywhere the same in x.
P.
It has p, right, but it doesn't, you cannot localize, plane wave is not a localized thing that is here in 1 second.
Probability density is the same everywhere, but there is
Right.
a probability current flow.
Yeah, there's a current flow.
Right, but then in this case, the thing that matters is you still cannot localize the plane wave, right?
Right, it's certainly not localized.
Right. So then so both that expression, the short expression here, that E equals P is not right. L equals T is also not right. Yeah.
One more comment on the velocity question. The P is related to the phase velocity, but would you say should be thinking about the group velocity of the wave packet?
Right, so wave packet is basically the correct picture to think about it. So we'll talk about that later. Okay, so that concludes the standard oscillation derivation. Again, hopefully you've seen this before. This is really I'm not creating these mistakes just by myself. These are really the standard derivation. And basically the upshot is that it is a two-level, essentially it is similar to a two-level quantum mechanics system oscillating. So that's very simple. But if you really think about it, there's a bunch of inconsistencies, as we've discussed. But it's quite interesting to think, why are all of these wrong? And again, there's other wrong ways to derive things, but basically all the wrong ways will get you the correct formula, which is an interesting feature. Okay, and again, what we'll discuss phenomenologically is we'll use this two-level system a lot, and hopefully this is something you've seen before. So for two-level system, which actually works pretty well for a lot of the experimental setup. So the feature is you have a mixing angle in front, sine squared 2 theta, and then you have delta m squared L over E dependence in the sine square. Okay. So, but the point is, given all the mixing angles and all the delta CP phases, this tells us how to compute all the oscillation probabilities. We can produce nu mu, measure them as nu mu, or measure them as nu E, or some other flavor, and we can measure things at different neutrino energy at different baseline. So all of this combination gives us the angles or the elements in a PMNS matrix. So this is a summary of the experimental progress that we've made since essentially the beginning of when neutrino oscillation was established. So typically, we write this in terms of the three mixing angles, the thetas, one delta CP phase, and as we've seen in the oscillation probability, it also depends on the delta m square. So we have three neutrino states. So technically, there's three different delta m square, but two have very different values. So we typically quote 2. And the point is to show that we have made a lot of progress. And for values like theta 1, 2 and delta m 2, 1, we basically enter sort of like a percent level or a few percent level precision. And the unknowns are, for instance, delta CP, still very badly constrained. And also, this you can sort of see theta 2, 3 also not so well constrained. So this is the summary of the experimental progress. Any questions at this point?
You have 2 lines because of this normal certain hierarchy?
Oh, actually not quite. So if you're talking about this line, then that's the significance level. 1 sigma, 2, or 3 sigma best fit range. I'll comment on hierarchy later. Okay, so that's the standard oscillation derivation. I'll come back to the mistakes later. So I'll briefly introduce basically the super crucial experimental measurements that established the oscillation, that really discovered neutrino oscillation. So there's really 2 sectors, solar neutrino and atmospheric neutrino. Are the sides okay? Can you see me clearly from? Okay. Okay, mostly because these experiments are really cool. So let's start from solar neutrino experiment. So the sun is powered by nuclear fusion, which produce neutrinos. So nuclear fusion, the way I remember it is, we probably all remember the interaction for beta decay, right? Nuclear fusion or nuclear fission is essentially this interaction. You move things either from left to right or to right to left, and then you put everything in the nucleus. So for instance, in the sun, because the sun has a lot of protons, one of the main interactions that produce neutrino is 2 protons fused into a deuterium and also gave you a new E. Or for instance, some of the element is kind of heavy. So for instance, you could have boron 8, which then,
I think in both of those lines you mean electron and antineutrino, right?
Thank you. So proton go to neutrino, go to new E bar. And this one is the opposite. So this is actually correct. So this interaction is basically proton go to neutron plus E plus nu, like this. Right. Thank you. Or for instance, boron 8 could decay to something plus positron plus nu E. So I guess essentially in the sun, you pretty much always have proton turn into neutron and then conserve charge and lepton number and put this in the nucleus. Essentially, that's this interaction. And so there's a bunch of these that all produce nu E. And the energy of these neutrinos, because these are nuclear reactions, the energy is in the, say, nuclear energy range. So it's about 0.1 to 20 MeV. And they're all nu E, meaning that there's no nu E bar or there's no any other flavors. Okay, and we sort of understand how the sun, is the powered by fusion reactions. And in the 60s, very early days in terms of neutrino measurement, 2 people got together and want to measure solar neutrinos. So one is John Bacall, and one is Ray Davis. Okay, and this story, I'm not sure how familiar you are, but to me, it's as a student, this was sort of the first topic that I worked on. I find the solar neutrino story super inspiring. So what happens is in the 60s, people wanted to measure solar neutrinos. And at the time, if you want to conduct measurement, what you need is first, the theoretical prediction of the flux. Second, some sort of detection method. Third, maybe the cross-section for the detection method. Right? Those are the basic ingredients. And at the time, they had none. So they wanted to measure solar neutrinos, and what they did is, in the same year, they had published a theory calculation of the neutrino flux from the sun. They also proposed an experimental way to measure things, and the detection channel to measure like a few MeV nu E. What they had proposed is this nu E would interact with chlorine and gave you an electron and argon 37. This is the detection channel they picked. And there's also no calculation for the cross-section of the detection channel. So they also computed that. So it's just really impressive that they basically did every aspect of these measurements. And they succeeded in computing things, and they built an experiment called Homestake. And the detection method I also want to make a comment on because it's just so wild. So if you know modern experiments and you look at this experiment, this interaction, what would your guess the signal would be in the detector? Again, this is a, let's say 5 MeV electron. This is obviously stuff at rest. Then what would you measure out of the electron? So if this were a modern experiment, I would say clearly we would just measure this electron. Back then, for reasons I don't know, I guess that's difficult. So what they decide to measure is not this electron, but instead they want to measure argon. How would you measure argon? Argon doesn't do much. And it turns out the way they measure argon is that argon really doesn't do much. That you would have a tank of basically cleaning solution of chlorine. And because argon is noble gas, it doesn't interact. So though once every month or so, you would filter all your liquid in your tank, and somehow that can pick out the argon atoms. And then actually it doesn't go to the ground state atom, argon, it goes to some excited state. And after you filter out all the argon atoms, you let it decay. And you count how many argon have decayed during some time. So that was a detection method that they came up with. I just thought it's amazing. Okay, so then within like a few years, they did all the theory calculation, build experiment, conduct a measurement. Yes?
How did they calculate this cross-section?
These are, I think these are like nuclear shell model sort of calculation. Certainly that's how one would compute that modern days.
The 60s, how would they do it?
So that I don't remember, but I suspect it's some easier version of the shell model calculation. Okay, and what they had measured is that the number of neutrinos they had experimentally measured is about a third of the theory prediction. Something like this. Okay, and this was obviously a problem. And again, they got this result in the 60s. And this is basically the first piece of the puzzle that eventually established neutrino oscillation. Okay, so that's half of solar neutrinos. And here I want to sidetrack a little bit, talk about another experiment, which did not measure neutrino oscillation for obvious reason, but I call it the coolest experiment ever proposed. So the solar neutrino experiment was in the 60s. So it was really in the early days of being able to measure neutrinos. So this experiment, I just want to talk about because it's really fun. It's in the 50s, and it was a proposed experiment. So at the time, we know that you can produce neutrinos from beta decays or reverse beta decays. So the obvious place where beta decay happens is nuclear reactions, right? So in the sun, it's fusion. In the 50s, there was a lot of nuclear reactions happening, and that was nuclear bomb testing. So Frederick Rennes, at the time, proposed to measure the following neutrinos at Los Alamos, where they were doing bomb testing. So imagine there's a bomb testing happening here. And in the proposal, there was a schematic drawing. And this is the explosion impact radius is labeled something like 30, 40 meters or so. And you want to measure the neutrinos coming from the nuclear bomb. Now, where can you put your detector? So this is ground, let's say. So first, you might think, I'm going to put my detector here because I want to measure neutrino flux. This obviously would not work because there's a bomb going off. So next, where would you put it?
Sorry, what's the 30 meters?
It's in their schematic proposal drawing. This is a nuclear bomb. I guess it's kind of the bomb impact radius or something. Or it's basically their illustration like, this is the bomb.
Oh, the bomb is that big.
Yeah, and they label something like 30 meter or 40 meter or so.
Okay.
And they say, okay, so I cannot put a detector on the ground because there's a bomb. So then I can put a detector underground, right? Like, what about here? this is, okay, so this is good because you shield yourself from the bomb, but it's still not good because when the bomb goes off, the Earth will shake, right? So the detector will also get shake in underground. So then their proposal is, let's still go underground, but let's do the following. Because Earth is shaking, I just need detector to be not touching Earth. So I'm gonna do this. I'm gonna build a tunnel or empty space. And the drawing is literally like this. I have a detector hanging. As soon as the bomb goes off, I'm gonna, let's say it hangs on Earth through something. I'm gonna release some opening. So then the detector will free fall. And in this drawing, they have some stuff on the bottom, and that's labeled foam and plastics or something like that. Right, foam and rubber. So then while the explosion is going off, you are underground, shielded, and not touching Earth, so there's no shaking. And it was supposed to land on some foam and rubber. So this was in the 50s. You see, people were still trying incredibly hard to see neutrinos from any source. And I actually just learned a couple years ago that this experiment, which was proposed at Lenode, actually got funded. Unfortunately, it wasn't built. But later on, Reines changed his proposal and actually set out to measure the neutrinos from nuclear reactor, which is, of course, a more sane source. But OK, so that's in the 60s. So
Were they actually planning to build a 30-meter-wide bomb?
well, so I think that's OK. So I think this is just what I remember from their schematic proposal. Whatever a testing nuclear bomb size, I don't really know. Right. OK, so, but OK, they didn't actually measure this neutrino, so didn't discover neutrino oscillation this way. But solar experiments they set out to do. And another important pillar to establish neutrino oscillation is atmospheric neutrinos. So this works like the following. So we have Earth atmosphere. Atmosphere is just a lot of nucleus. And let's say we have high energy cosmic rays. Let's imagine these are just protons. And so essentially you have a proton nucleus or proton-proton collision, which give you a lot of pions. Charged pions, neutral pions. And let's say one of them is a pi minus. Let's pick this guy in the middle. Pi minus would decay, right? So it would decay to a mu minus. And sorry, mu minus is now bar. It's on the side. Mu minus and a new mu bar. This muon would also decay, right? Muon is also not stable. It will give you a E minus, E bar, and a muon. So I think I conserve charge and lepton number. So this should be the decay chain. So the point is that cosmic rays are very energetic, tens of GeV and blah, blah. So, and these pions are also pretty energetic. Imagine there are at least GeV or so. And so then you would produce something like GeV neutrinos. And the flavor ratio from these decays should be that nu mu to nu e, and I'm counting neutrino and anti-neutrino. Nu mu and nu e should be roughly 2 to 1, right? Because look at this decay chain. I got a mu plus, I got a muon neutrino and anti-neutrino, so that's 2, and the electron neutrino. Let's say it should be about 2. And this is not exact because in the atmosphere there's other things decaying and things happening at different height and stuff like that. So there's details here, but roughly speaking, this roughly works. Okay, and Kamioka tried to set out to measure this thing. So measure this ratio. And they observed the following. So, well, this Earth is really not sphere. Okay, so this is the Earth. And let's say the detector is, here. It's very close to the Earth's surface. So you can measure this ratio from neutrinos coming down, right? And basically, where the neutrino is produced in the atmosphere to the detector, roughly these neutrinos would have traveled about tens of kilometers. And they measure this ratio, and it's very close to 2. Okay, good. So that means our modeling of atmosphere is basically okay. And then they can also measure the neutrino coming from below, right? Like this. And also on the side, I guess. But anything that's like not down going. And here, the length of neutrino travel is somewhere between 10 to the 3 to 10 to the 4 kilometer. Depends on where it is, but roughly at least a couple or more magnitude than this. And in all the directions, they measure this ratio. It's not 2. It's something like 1 to 1.5. Okay, so basically what happens is that we had 2 experiments with various convincing level that both had measured less neutrinos in some sense than our theory prediction. And was there a question? Okay, and this was initially happened like in the 60s. And it just took, there's various, initially people just didn't believe the experimental measurements, like for the solar one. I mean, I would say rightfully so. If I hear someone carry out this experiment, I will also be like, are you sure? It's just, and then this is one part that I really find inspiring about these studies. So again, this was my first like a student project, and I just remember there are so many things happening in the sun, and also there are so many different effects that could at play. And whenever you think of an effect that may change the neutrino flux or something, you can find a John Bacall paper that had explained this effect and had estimated the corresponding uncertainty. So basically, the point is, since the first measurement, there had really been a ton of work that went into really quantifying the uncertainty, both on the theory and experimental side, trying to convince people that they know that this is a real problem. And it took so long to convince everyone. And let's see. Okay, so let me use this board. Eventually, yeah.
You also have solar neutrinos for Capitan, right?
Great question. So, right. So the question is, we also measure solar neutrinos in Kamiokande. That is correct. So this is more like the historical measurements in both detectors that, for instance, the atmosphere one actually got the Nobel Prize. And I'm about to say the snow one. So right now, Kamioka has both measurements. Super K has both measurements, the atmosphere and solar. But they are quite separate in that, the neutrino energy is completely different. Right, so solar neutrino, you're having like MEV interactions. You have MEV stuff in your detector, whereas atmosphere, you have like GeV neutrino. So it's not like, even in Super K, it's not like you would mix a solar neutrino with atmospheric neutrino. Yeah. Okay. So I think in terms of convincing people that really, there's something fishy going on and neutrino oscillations seem to be a good explanation, I think the atmospheric one was fairly convincing because they had measured, basically you have more control systematic. Right? You already start out to measure a ratio, which has less theoretical uncertainty. And you also measured one direction that is consistent with theory. So if you look at, Kamioka has this famous plot in terms of looking at this ratio as a function of zenith angle, and it was fairly convincing. And on the solar side, I think it was just really hard to convince people that we can compute the solar neutrino flux. So really, the actual experimental confirmation, which I think truly convinced everyone, was solar neutrino measurement in snow. And this is super convincing because the way is, if you want to convince people that why do you only measure a third of your predicted flux, and your explanation is oscillation, which means that 30% of them remain as nu e, but then the 70% of them sort of turn into nu mu and nu tau. How would you convince people that is the solution? Is you have to design an experiment where you can measure nu e flux, nu mu flux, and nu tau flux. And in the end, they couldn't measure nu mu and nu tau separately, but they can measure this. So really, the incredible experimental design of SNOW, which I don't have time to talk about, is that they measured nu e flux and nu mu and nu tau flux. And of course, what they have seen is the total is consistent with theory. So then it definitively proved that the missing 70% went to something else because of oscillation. Okay, so that's why, right now when we talk about datum square and also a lot of missing angles, people still use the phrase the solar sector and the atmospheric sector, because those are the two, I guess, pillars that essentially established neutrino oscillation.
How do they detect the mu and tau neutrinos?
Great question. So
Did they detect them as being different, or did they just set up something that could detect any of them and would activate?
So what happens here is they detect neutrino through neutral current interaction. So the neutral current interaction, I think, goes like the following. Something neutrino plus deuterium goes to proton plus neutron. I don't think I missed anything in the interaction. So this one, it's neutral current. So it basically gave you the sum of neutrino flux, right?
So this only detect electron neutrinos?
So deuterium is a proton plus neutron. So really the only thing happened, kill out neutrino. So it's just you break up, you provide some energy and break up deuterium. Sorry? Yes, so it's Z exchange. So they have multiple detection channels. Some of them are through charge current interaction, so W exchange. And they have this channel that detect through Z exchange.
Okay, so they didn't have a mechanism that detects specifically, say, mu neutrino.
That's a great question. So it's impossible in solar because the neutrino energy is, again, something like up to 20 MeV, right? If you want to use this neutrino, let's say muon neutrino, interact with whatever, give you a muon, there's just not enough energy, right? Assuming this thing is something sitting at rest, right? So it's not possible to see charge current interaction for nu mu and nu tau. So the best thing we have is a neutral current interaction. Yeah.
These ratios are energy dependent, right?
You mean the atmospheric one?
In general.
Yeah.
So
Could you repeat the question?
energy range that they were looking at in physics?
Right, good question. So the first question was, so these ratios, and most things I talk about, has energy dependence. I just simplified that here. But for instance, for the atmospheric sample, it was also fairly convincing that they had looked at sub-GeV, multi-GeV, and highest energy. And for the different energy samples, they had seen basically different kind of this behavior. And of course, that it was consistent with what we expected, basically the L over E thing. Right. Okay. Any other questions? No? Okay, so that's basically the confirming measurements of neutrino oscillation. So one thing I want to make a comment on is that, and especially because later I want to draw a comparison to our current neutrino experiment. So at this time, these are fairly big effects, right? So this thing, oscillation, is so strong that it suppressed majority of your flux. So here you're trying to measure effect of 3 effect, which is pretty significant. And similarly, in the atmospheric sector, you are looking at something that's still effect of 2 to 50%. So these are huge effects that we're trying to measure. And of course, since then, we built a whole bunch of experiments. Trying to measure oscillation in many different ways. A good way to summarize it is this plot. The baseline of the experiment, log L, oh actually, the energy of the neutrino beam, log E, and the baseline of the experiment, log L. And this of course is I'm just talking about a range. For instance, like a solar neutrino, it's not like a neutrino is at one energy. There's a little range. But roughly speaking, if you put most of the experiments in this plot, actually all of the experiments in this plot, they mostly fall along 3 lines. So something like here, here, and here. And experiments are like, like this, and a bunch here in some scale. And you can understand why looking at the formula on the left. So you want to pick your things, because we only have this many delta m square. So you want to set up your experiment so that the delta m square L over E is roughly of order 1, right? So most of these fall along like the bottom line roughly corresponds to the smallest delta m squared that we have, which is also called the solar mixing. The value is 7 times 10 to the minus 5 eV. For instance, reactor experiments nowadays, a lot of them is kind of sitting here. The other line is the bigger one we have, which is the atmospheric delta m square. And this has a value of about 2 times 10 to the minus 3 eV squared. Oh, delta m square, eV square, I forgot that. And this is like basically most of it, like a long baseline experiments, like NOVA, T2K, DUNE, Hyper-K, sort of sitting on this one. So long baseline nowadays. Okay, yeah.
So I'm just a bit confused. What is the relation between these delta m squares atmospheric solar to the delta m between the different flavors of the neutrinos?
Good question. So I think the question is, what's the relation between the delta m atmospheric to the delta m that I just mentioned there, right? Right, so this is convention. So the delta m solar square, which is delta m 2-1 square. I'll explain that in a little more detail. And delta m atmospheric square is delta m 3-1 square, 3-1 or 3-2. So solar is between 1, 2, and the larger one has a 3 in it.
But they're somehow more, the atmospheric experiments are more sensitive to the 2, 3 and the solar to the 1, 2.
Correct.
So historically, that's why they're called like that.
Exactly, right. And I think nowadays it's equally popular if you see that people write this as solar or like 1, 2 or 2, 1. Yeah.
So you're not plotting data, you're plotting like experiments that have been built.
Correct. So right. So every cross here is one, roughly speaking, is one experiment, and I'm just explaining why. If you talk about a neutrino experiment, there's a reason that people pick certain baseline for the experiment. And typically, the reason why baseline are certain length is because of this. So roughly, you want your quantity in the sine square to be of order 1. And delta m squared, we don't choose that. That's what the value nature gave us. And the energy is also, there's limited range you can manipulate energy. For instance, we use neutrinos from reactors. They're just a few MeV. You can't really make them higher or lower energy, right? And accelerator, we typically just produce like a few GeV neutrinos. So energy is also more or less, if you pick a source, there's limited range, you can manipulate that. And so we typically pick a baseline so that it falls along a specific line.
Does the original Ray Davis experiment, where does it fall? Because they didn't choose E or L.
Great question. And for solar, things do not work like this, because for solar, the oscillation is actually controlled by matter effect, which is, this is vacuum. So I'll talk about matter effect later. Yeah.
What if we know that the sign of the solar documents?
Great. That is also, so how do we know the sign of solar? So that is also from matter effect. I will get to that after this.
So should I see like this relation like just
Yeah, so let's for now just say these are absolute values. Okay, and so there's a third line, right, that also has a bunch of experiments now. So they roughly corresponds to delta m squared of 1 EV squared. And the reason is you might have heard that we have this so-called, I guess, short baseline anomaly or some other names as well. So there are some anomaly in the data, in oscillation data. And I'll talk this more in detail in the third lecture. But essentially, they are possibly hinting at the existence of a stereo neutrino with mass splitting difference with the standard one at about 1 EV squared, which is why, and this is something that, of course, we want to confirm or reject. So a bunch of experiments trying to measure this 1 EV stereo neutrino sits at a different baseline. But essentially, all experiments we have are picked so that they are sitting at a specific delta m squared. Any questions about that? Yeah.
So when you labeled delta m solar squared and delta m atmospheric squared with corresponding 1, 2, or 2, 3, is that assuming a particular hierarchy?
No, great question. So let me write down all the mixing quantities. Okay, so first let me define what is mass hierarchy. Okay, so first, what can we measure from the solar oscillation? What we measure is, it's really well approximated by a two-level system between 1 and 2. So from solar experiment, we know the mixing angle. So from two-level system, you see you get one mixing angle and one delta m squared. From solar, we know theta 1, 2. And delta m 2, 1 squared, this is how it's defined. And also delta m solar squared, like the following. And what we know is this thing is positive, meaning that, let me draw here, meaning that 1 is lighter than 2. So 1, 2. From atmospheric sector, again, these are the early sectors, it's really also pretty good, well approximated by two-level system, and it's the 2, 3 sector. So from there, we know theta 2, 3. And also, you either call it delta m atmospheric square, or depends on the mass hierarchy, it's either delta m, okay, so I don't know what sign to here. It's either delta m 3, 2 square, or delta m 3, 1 square. But which one it is, it doesn't really matter, because this difference is so big, it's kind of like this. 3 and 1 and 2 are very, very different. We don't actually know the sign of this, which means it's either this oriented in mass, or it can be 1 and 2 are very close, but 3 is lighter. And so which orientation it is an open question. So this is called normal ordering or normal hierarchy. And this one is called inverted ordering or inverted hierarchy. And we don't know which one it is, which means that we have not measured this value accurate enough to be sensitive to this difference. So in some sense, it doesn't really matter which one you call it. Yeah.
But we know it's between 2 and 3 because you're at theta 2, 3.
Correct. So, okay, so I think there's also the basic how you, right, so the question is, I guess, because here you call it theta 2, 3, and here which one it is. So I think there's also the defining, like, what do you define as 2 and what define as 3? So I think there's also basically freedom in how you define things. Because theta 1, 3, theta 2, 3 is very close to 45 degrees, right? So it's really, if you look at the flavor content, it's also basically half and a half. So there's no way to know the difference.
Okay.
Yeah, I don't really want to get into that.
Okay.
Yeah. Yeah.
We don't know the sign because it's sine square,
Right, great question. So the question is, why do we not know the sign? So again, it's super lucky that, in the early solar and atmospheric days, things are well approximated by the 2-level system. So this tells us a lot. So this tells us because it's a sine square dot m square, so in principle, you should not be able to tell the sign of dot m square, which is why in the atmospheric sector, we still don't know. And that's why, mass hierarchy is one of the important things that we're trying to measure with next generation experiments. It's actually very hard to tell them apart. So rather, the question is, let me finish the list. So these we have measured. And then reactor experiment, which I didn't talk about, tells us what is theta 1, 3. So that we also know. And I think the only other parameter that we don't know yet is delta CP. And I'll comment on delta CP later. OK. So now I want to explain, since by default, we should know the sign dot m square, how did we figure it out for solar? And this generally goes by a name of matter effect. And the concept is very simple, that when neutrinos are propagating in matter, the equation of, let's say, the equation of motion changes. So then our naive derivation of the oscillation no longer works, and it gets modified. So the simplest way to see this is the following. OK. So let's basically recap that calculation, now only using 2 flavor, but solve it a little bit differently. So really what I was solving is I just mass eigenstate go as, the eigenstates in vacuum. And so for wrong reasons, but obviously one important ingredient is I need to substitute my L with T or T with L. So I'm just going to do, instead of D over dt, I'm going to change into L. And also this is supposed to be energy. But we know that let's use this equal momentum assumption. So I expand energy in terms of momentum, and the remaining piece is this. So this gives me the correct oscillation formula. OK, so this is solving things in mass eigenstate, which is what we did. But let's rotate it into flavor basis. OK. Nothing complicated here. I'm just going to rotate this expression to a different basis. So looks like the following. So now I'm rotating now I'm evolving a flavor basis, flavor state. And I pick up some, elements of the mixing matrix. So U beta I and the mass square difference, and U alpha I star, U alpha, something like this. Again, nothing fancy. I just changed the basis. So then let's assume that in solar, we just have a two-level system. Let's call it nu E and nu mu. Yeah. Right. So the question is, shouldn't there be more terms? Basically, yes. So what I initially, if I don't expand anything, this term should just be energy of eigenst I, right? So what I expanded is just like the derivation over there. I assume they have the same momentum, so it becomes momentum plus this term, right? And if things are same for all states, it doesn't add to oscillation, right? So then I just, which is also, you can see it more explicitly in that derivation. Here, I have ek minus ej. So anything in common just drops out. So I just ignored the common term. Yeah. Okay, any other questions? By the way, I felt alarmed after Lloyd's lecture because I felt like I had prepared too much material. I'm happy to report I'm at about 40% of what I thought I would cover in one lecture. So this has been fun. Okay, so I'm just going to write that a little nicer, but no difference. So let's say two flavor. I'm just going to call things nu E and nu mu. And in solar, you can just imagine this nu mu is some mixture of nu mu plus nu tau. And the two mass eigenstate will be like 1 and 2, nu 1 and nu 2. So then I can clean that up a little bit. So my evolution of my flavor states looks very nice. It's just del m squared over 4e of minus cosine 2 theta, sine 2 theta, sine 2 theta, cosine 2 theta of nu E, nu mu. Okay. So again, I really am not doing anything different from there. I'm just evolving things in vacuum, pick up a phase, and instead I write things in flavor basis. So this is the free Hamiltonian in vacuum, right? In flavor basis. Now the key about matter effect is that when there's matter, Hamiltonian pick up an extra term. So there's the free one, vacuum, plus something called matter potential, like this. And this potential is only there for electron neutrino. For nu E, and it's not there for the mu tau component. And this is really the thing that breaks the symmetry between 1 and 2, and this allows you to see the sign. I'm going to derive this in a second. So any questions about this part?
We were wondering why the rotation matrix has a -1 determinant this way.
Oh, sorry, could you repeat the question?
The rotation matrix there seems to have a -1 determinant.
The minus be on one of the signs instead of the cosine.
Great question. First, I don't think that's, okay, interesting.
It goes to 0. It's not exactly. Yeah, typically it's the upper right that has the minus sign on the rotation.
Right, okay, so great question about the overall determinant. I don't know, maybe I missed a sign somewhere. But it's not the typical rotation in the sense of typical rotation is cosine, sine, right. But it's one angle, it's just theta. So here, everything is cosine 2 theta, sine 2 theta, sine 2 theta, cosine 2 theta. And the reason is this is essentially two rotation matrix multiplied together. So let me look up the determinant issue. But this is not the normal rotation. It's two of them, essentially.
Addition formula.
Right. So that's why I meant it's not cosine minus sine.
But like the composition of the rotation is still a rotation. So the determinant.
Yes, I agree with that. So I probably missed a sign somewhere. I'll check that.
I think you are taking one matrix, because you have m1 squared and 2 squared in the diagonal.
Yeah.
I think you are like subtracting.
Yeah, it could be. Like, I'm not sure whether this is 1, 2 square or 2, 1 square, because right now this guy has a sign. So let me just look up the convention and, yeah. Okay, any other questions?
Got about 10 minutes, by the way.
Yeah, I saw that. Okay, so let me just briefly explain what that potential term, or it is called a potential, what that term is. So essentially, let's think what is, inside the sun. We have protons, neutrons, and electrons, right? So incredibly high density of these stuff. And again, I'm talking about MeV neutrino propagating. Essentially, they pick up imagine it's coherent forward propagating. So it's kind of like when photon propagating in medium, it pick up a mass. It's very similar effect. So then we can write, let's just use for Fermi interaction because energy is very low. And I can rearrange the normal Lagrangian term into something like this with fierce transformation. So now I turned it into a current-current interaction. So what this is saying is that this is describe how my neutrinos are propagating. And if I have let's say a uniform electron background, then I can integrate it out. I can look at the expectation value of the electron term. This will have expectation value, right? So the simplest thing to think about is if I pick gamma 0. If it's gamma 0, then this is just E dagger E, which counts, which is the number operator, which just counts how many electrons are there. And you can convince yourself that when the mu is not 0, it's something with like the momentum or the velocity of the electrons, right? And let's consider electrons sitting there not doing anything, so it doesn't have a velocity term. So the only thing that's present is the number density of the electron. And this only tells me how many left-handed electrons there are. The sun's not polarized, so I should have twice. I should also have the same number of right-handed electrons. So then this expectation value is this. And what this term gives you, what this term does, is, if we were trying to solve remember the kinetic term for a neutrino, looks something like this, right? And you see that this basically has, the similar look, just with something else. So this tells me that if I were to solve the equation of motion for the neutrinos, it's going to get basically the same as before, but get modified by this additional term. So the equation of motion, instead of the normal Dirac equation, it picks up like this. G Fermi, electron number density, gamma 0, this. So this is a normal term. I'm skipping mass for now because it's very small. But the important thing is it picks up an extra term. So this is very similar to say for neutrino to travel in medium. So it picks up, this is normal momentum and a term that's proportional to square root G Fermi electron number density. So it's just like photon pick up a mass when they travel in medium. Exact same thing. And so then when you put this into this sort of derivation, it manifests itself as a term like this, and it's typically called matter potential. Although it's not, I don't know, to me it's not quite a potential. But in the quantum mechanics derivation, it sort of looks like a potential. And the potential value is just square root G Fermi electron number density. Okay, so we can just finish this, which is not bad. Okay, so now I still have a 2x2, I'm trying to solve a 2x2 matrix thing. Except for a weird, maybe minus determinant, we can solve that. And I'm just gonna write down the expression because I want to compare to the 2-level 1 in vacuum we have. Like this. So once I consider this extra piece, my solution becomes, actually, let me write it here. P alpha beta. Okay, so I still have the sine 2 theta square term. That's like the vacuum case. And I still have something that's sine square delta m over L over E, 4E. So just like that, but I got additional piece like this. 1 plus c squared minus 2c cosine 2 theta, I think. And also overall, I have 1 plus c squared minus 2c cosine 2 theta. And this c is something like some combination of the matter potential. 2 square root 2 G Fermi number density of electron delta m squared. So no absolute value, just delta m squared over E. Okay. The point is the following. If the sign of delta m squared is plus or minus, that will give me the c value of plus or minus. And then you see here, it's the c or plus or minus, it would actually make a difference on the value here and here. So this is really the way why we know the M1 is lighter than M2. It's the only sign of delta m squared we know, and it's come from matter effect. And right. And another thing that you might notice is that, so for the 2-level oscillation probability, the solar actually is in the range. That's why is the L for, what is the L for solar? It doesn't matter, because in the sun, the production region of neutrino is so large. It's on the size of like radius of the sun, which is much bigger than the size of Earth. We experience basically L so many different times that it's like an averaged oscillation probability. So if you average a sine square, you get half. So naively, if things were in vacuum, the oscillation probability for a solar neutrino would have just been half sine squared 2 theta. And you will see that's a problem, because half sine squared 2 theta is smaller than half, right? Because sine squared has to be smaller than 1, which means that the new flavor, the nu mu and nu tau, cannot be more than 50%. Whereas when we detected, only 30% survive, so 70% turn into new things. And that was one of the things that puzzled people at first, because it's a pretty straightforward argument. And regardless of mixing angle, you should not expect 70% of flux has turned into new things. And that was very puzzling. And until we figure out the matter effect. And you can see here, it's sine squared, something that might get averaged, but then we're dividing something that could be bigger than 1, right? So this tells you that the average oscillation probability can be smaller or bigger than, naive estimate. Okay, so I'm coming up to the end of time. I just want to make a comment that, sorry for keep lying to you in the lecture, this is not actually how solar neutrino oscillate. How it actually oscillates goes by something called MSW effect, which I won't have time to go into. So the real part about, the true part about the derivation is that it does rely on matter effect. And this does show why you are sensitive to the sign of delta m squared, and how things can be smaller than, the appearance possibility can be larger than half. But exact math is definitely not correct. Okay, so I guess tomorrow we'll pick up more finishing the oscillation stuff. Thank you.